Can you please tell me what is equipotential surface? It is the surface in the electric field which is everywhere perpendicular to the field lines. Yeah. Here, with E bar as the electric field intensity, and dl bar the differential vector on the surface, E bar dot dl bar is equal to 0 at each and every point on the surface. Correct? If E bar dot dl bar itself is 0, why? Because E bar is perpendicular to the surface and dl bar is the differential vector on the surface, because of which they are mutually perpendicular. Dot product of two mutually perpendicular vector quantities is always 0. If E bar dot dl bar is equal to 0 at each and every point, the potential difference between any 2 points on the surface integral A to B E bar dot dl bar is equal to 0. Because E bar dot dl bar itself is 0, integral of 0 is 0 only because it is definite integral. Is this clear? One more point that we should remember is if the field is conservative, is what actually? Practical, not the one just given. If the field is conservative, the potential difference between 2 points, any 2 points, is only the point function, to say that not a path function. We saw The potential, yesterday we discussed it, today we are just consolidating it. Let us suppose A and B are 2 points. A, B. This is path 1. This is path 2. VBA along path 1 is equal to VBA along path 2. If we reverse path 2, it results in a closed path A, B, A. Now, integral around the closed path E bar dot dl bar is equal to, I'm just taking integral only. Minus, I'm not worried because it is a closed path. Integral A to B along path 1, E bar dot dl bar plus integral B to A along path 2, E bar dot dl bar. You agree this? This is equal to VAB if I put minus everywhere. Now, VAB again minus will give what? Plus VBA, which is equal to VA because the path is reversed. You agree this, no? VAB is what actually? 1 second. VBA plus VAB, which is VBA minus VBA equal to 0, because of which in any conservative field, so in any conservative field, integral around a closed path E bar dot dl bar is equal to 0 is actually KVL used in the network analysis. Please check. Yeah, one more thing, I'll finish it off now itself. Then we can go to capacitance and all. Next point. Poisson's and Laplace's equations. Poisson's equation is what is required for us to understand the electrical behavior of a p-n junction or any junction between two dissimilar material. This actually, Poisson's equation relates potential and charge density at any point. Because it is very simple to derive, I will take it up now. Given V, the potential at any point, given V the potential at any point, we know that the electric field intensity at any point E bar is equal to minus del bar V. If epsilon is the permittivity of the medium, T bar is equal to epsilon E bar, correct? At any point. At any point, D bar is equal to epsilon E bar is equal to minus epsilon del bar V. Del bar V is a vector minus into multiplied by minus epsilon. If D bar is the displacement flux density at any point in the field, the volume charge density at any point is rho V is equal to del bar dot D bar is equal to minus epsilon del bar dot del bar V. Any E bar dot E bar, any vector dot vector is vector square, magnitude squared actually. Because of which rho V is equal to minus epsilon del squared V implies del squared V is equal to minus rho V by epsilon, to be remembered as the Poisson's equation. Check it once. So if you know the volume charge density at any point in the region whose permittivity is known to you, that immediately tells you the value of del squared V. In Cartesian coordinate systems, del squared is what? In Cartesian coordinate systems, del bar is equal to dou by dou x ax plus dou by dou y ay plus dou by dou z az is known to us. Del squared is dou square by dou x square plus dou square by, because it is del bar dot del bar, plus dou square by dou z squared. So if V of xyz is the potential at any point, dou square V by dou x square plus dou square V by dou y square, because it is del squared V, just multiply, plus dou square V by dou z squared is equal to minus rho V by epsilon, is the expanded version of Poisson's equation, which we want to start the electrical behavior analysis of p-n junction. In the region where rho V is equal to 0, we know that potential can be there everywhere. Potential can be there everywhere in the charged region as well as uncharged region. We know that. Some point charge is there, somewhere also, everywhere there is a potential. And there can be potential at the point where field is also, the charge is also there. In the region where rho V is equal to 0, Poisson's equation becomes del squared V is equal to 0, called as Laplace's equation. Correct. In the junction region, no, there is something called as depletion region where immobile ionic charges will be present. The volume charge density of that region is known to us because we know the doping concentrations. Through that, we calculate E and the potential difference between the ends of the junction. Please check it. These are the things that we want to know as a concept in potential difference, gradient, right? Poisson's equation, where it is to be used, and the Laplace's equation.